So before we get started on the overall discussion, I want to just give you a little bit of background about what I'm doing and why I'm here. The National Center for Timber Durability and Design Life was started about 2 years ago, and it's based out of the University of the Sunshine Coast. And it has a group of partners. The University of Sunshine Coast is a primary host, but the University of Queensland Engineering Group is involved, and the Queensland Department of Agriculture and Fisheries are our two main partners. All of this is funded by the Forest and Wood Products Australia, and the goal is really to kind of regenerate durability research in Australia, which has kind of fallen off the table here. Two of our newer partners are University of Tasmania at Launceston and the University of South Australia. So we're always looking for people to work with. These are just some of our partners right now. The center has a 5-year mission, just like the enterprise did many years ago. And it has a group of objectives that it's seeking to look at. And they're sort of motherhood and apple pie in terms of we really want to regenerate what was once here. Australia was a world leader in durability research, and many of the activities that went on 20 years ago are still relevant today, but there's been a disinvestment, and so the center is there to try and reinvest in the research and also to try and help people use timber better. So that's sort of our main goals. We have a group of people now we're assembling both at USC, University of Queensland, and DAF, as well as our partners, UTAS and UniSA. And we're hitting lots of different areas in engineering, fire science, timber durability, biology. So if you have questions related to timber durability, we hope you'll contact us. That's what we're here for. As we get into dealing with materials, it's important to understand that while everybody seems to understand wood, everything degrades. And when you design with materials, it's important to understand those limitations of the material and to design for an expected life. So steel corrodes, concrete will spall, wood decays. We all sort of know that. With wood, it's a little bit different because it's a biological organism. And so before we get into sort of the discussion of what happens in attacks wood, it's important to understand what we look at. And if you look at this cross-section of a piece of Douglas fir, which is also called Oregon, you'll see that it's got sapwood, heartwood, and the pith. And in this case, there's rings for tree growth. But if you look at the light-colored wood, that's the sapwood, that's the living part of the tree. And the orange-colored wood is the heartwood. And these woods don't have different structural properties, but they have very different durability properties. And so it's important to understand there are differences across this cross-section that can affect performance. If you look closer at the timber, and this is a scanning electron microscope image, you can see there's lots of tubes. And essentially, timber is really just a collection of hollow tubes. It's an incredibly efficient structural material for supporting tensile or loads in tension and compression. And it's a mix of polymers. And the polymers are cellulose, lignin, and hemicellulose, and they're all mixed into what we call a matrix. And to get at the original, to understand how they all fit together, people are still working on that. But basically, each one of the polymers serves a different purpose in the structure. The main thing we need to understand about timber in general is that it will tend to absorb water from the atmosphere and also when you put water on the surface. And that water will swell the wood and it weakens it slightly. And so water becomes incredibly important in timber, and understanding it and dealing with it is an important part of using timber properly. And if you think about the structure of wood, this schematic sort of describes wood as sort of reinforced concrete. If you look at cellulose, which is the long chains of polymers in the wood, they're kind of like the rebar in concrete structures. They give wood the tensile support it needs. And then the lignin and the hemicellulose are kind of wrapped around that. And they all behave as a unit. And we want to make sure that unit stays intact. Water is probably the biggest enemy of wood. And if you look at water and wood, we talk about two different types of water. And it's important to understand them, even though it seems like, why would I need to know that? I'm just going to design with it. But we have what's called bound water and we have free water. Wood will absorb water from the atmosphere to the structures, to the polymers in the wood. And that water we call bound water. You can't extract it from the wood very easily. You can oven dry it, you can dry it and get the water out, but it's really bound with the cellulose in itself. The free water is the water that's liquid in the cell wall. And when we look at properties, the points between where bound water and free water change, where you've gotten all the bound water you can get, and now you've got free water, we call the fiber saturation point. Bound water has some effects on properties that you need to know when you design. It swells the wood, so you need to understand that as wood dries, it will shrink. As it gets wet, it will expand. And when you build buildings, you account for that shrinkage in your designs to make sure you don't have gaps or having excess swelling on the material. As you wet wood from 0 to 30% moisture content or thereabouts, it actually gets a little bit weaker. And so when you design with timber, you design for wet use and dry use, and that's why you do that. It also affects conductivity and insulation, but really what we look at are its swelling and the fact that properties will change. As I mentioned, there's the fiber saturation point, which is sort of the magic point where there's no free water present in the wood, all the water is bound. And that point it varies with wood species. I've listed some here, and I apologize for not having any eucalypts. I just couldn't get them in short notice, but you can see that we tend to say that the fiber saturation point is around 30%, even though we know some woods, teak, rosewood, western red cedar, are lower, but that's a good ballpark figure. That's important to understand. Free water is the water that comes after that. So going from 28 to 50%, all that water is going to be liquid. And you can squeeze it out of the wood. You can literally take wood in a vise and squeeze water out of it, very wet wood. The free water is going to affect things like thermal conductivity. So the wet wood will transfer heat more rapidly. It will obviously change the mass. It's going to weigh more. The biggest thing we worry about, though, is it changes the durability of the material, because now organisms that normally wouldn't be able to attack wood can do so. So one of the questions we often get is, my moisture content in a building, let's say I'm in Cannes, and I've got a really humid environment, it's really warm. Can I get above the fiber saturation point with just high humidity? The answer is no. So if you look at this table, which is out of the Forest Products Lab in Madison chart, you can see that and I apologize, but if you go up to 32 degrees Celsius, which is Cannes sort of, and you look at 90% relative humidity, the moisture content is 19%. So in most building situations, you shouldn't have free water in the wood unless you have condensation. And so if you have a cold surface in a very humid environment, then you will get liquid water. But normally with well-ventilated buildings where you deal with moisture in the air, you should not see moisture conditions suitable for decay. It's important to understand because it comes back to one of the controls we'll talk about later. So let's talk about what attacks wood. So one of the biggest things we'd look at is whether it's living or non-living. So abiotic damage is caused by non-living agents, as we say. And we look at things like sunlight, which is actually quite destructive on wood. The ultraviolet energy in light will degrade the wood on the surface. And you can see this picture on the right shows a piece of western red cedar, and the surface is quite heavily grayed and weathered, and some people find that attractive. But if you pull the wood away on the surface, you can see it's quite sound beneath. That's weathering, and weathering is we'll talk about in a second. You can also have mechanical damage, and that would be something like a stair tread that gets repeatedly subjected to load, or in places where wooden sleepers are still used. Railway sleepers are a classic example of where mechanical damage is very important. You can get chemical damage where you get excessive chemical exposure, and not many places where you'll find that, but chemicals can degrade wood. And then finally, heat. And we worry a little bit about heat damage when we get into environments where there's just very high temperatures and the wood cellulose, the polymers will decompose. But mostly we worry about weathering because it is by far the biggest problem in timber in terms of appearance. So as I said, sunlight contains energy, it releases into the wood. As it does that, it creates free radicals, much as it does on your skin when you get suntan. Those radicals will tend to attack the lignin, which is the most susceptible, and that slow process gradually reduces the surface of the wood. The process begins within 24 hours of exposure, and it's one of the reasons why when you're going to coat wood, you want to do so relatively soon after you put it in. And this is just kind of a schematic showing what happens when you have sunlight. It just gradually sheds the surface. It will degrade the softer parts before it degrades the harder parts of the wood, and so you might get a kind of a corduroy or rumbled effect on the surface. Weathering is probably the most critical non-living or agent of damage to wood, because most timber is removed because it doesn't look good. We all know that wood burns. I'm not going to talk about that because I think many of you understand that wood burns at a very controlled rate, and actually being in a timber building in a fire is actually quite safe if it's constructed properly, because you can get out in time. But let's talk about the biotic organisms. So biotic organisms are those that are living agents, and we look at bacteria, fungi, insects, marine borers, pretty much anything that can get at all the energy that's in the wood, we'll try to. Luckily, not too many organisms can get into wood, and we're quite fortunate about that because it's very resistant to degradation. I'm going to stick to the fungi and the termites because they're the most important ones in Australia. And most everybody here has dealt or experienced termites, and termites are wood utilizing organisms. They live in large colonies. They are amazing insects, if you want to look at them that way, social insects with a very highly organized structure. In Australia, Australia is blessed with many termite species. And this map from CSIRO sort of shows you the hazard of termites in Australia. And if you look at the map, you'll see blue is very low. And you'll notice that Tasmania is not there. It's not because we don't like Tasmania, it's because Tasmania has no economically important termites. The rest of Australia pretty much does, and if you look at where the termite hazard is, it's pretty much along the coast, which is where everybody lives. So termites become very important, and there's a number of different species, but they're social insects. There's a queen, there's caste system. Colony sizes can go anywhere from 7 to 50 West Indian drywood termites, all the way up to 4 or 5 million workers in a colony. So they can be very destructive in very short periods of time, and they're common all across the country. They typically leave signs of their infestation: mud tubes going over structures, softened wood, wings on the surface of the material. Generally, you find termites becoming more important as the building ages. Freshly constructed buildings tend to be less susceptible because in building the building, you've disrupted the area so much that you probably don't have many termites. But as the neighborhood ages and termites start to move in, the risk of termite attack becomes higher. They're very important. The other organisms we worry about are fungi, and fungi are divided into a number of different groups. We have mold and stain fungi, which attack freshly sawn timber. These are two good examples of really moldy stained wood. The one on the left is mold, which is on the surface of the wood. The one on the right is more stain, which goes deeper into the wood. They both live on sugars stored in the wood, so they don't cause a lot of structural damage, but they cause a lot of visual issues with timber. And they're a sign that the wood has stayed wet far too long after the tree was cut. So as I said, mold and stain fungi require some free moisture in the wood. They can grow at moisture contents as low as 20%, and there's a lot of debate among the researchers about whether they can grow at lower moisture contents. I am of the opinion that they grow where there's condensation at some point, and it really doesn't take very long for mold to grow. You can get spores on the surface of a piece of material within 24 to 48 hours after they start growing. So they're very aggressive and they're very opportunistic. They land on almost anything. Many of the species that you would find of mold species are those you find on food as you would on wood. They tend to be active at higher moisture content, so faster attack when the wood is wetter. They may be present when the timber is cut, but they definitely come in thereafter. And it's important to understand that when you look at wood and you look at the risk of things landing on it, spores from fungi are always in the air. We always have spores around. And so if you create conditions that are suitable for growth, like freshly cut timber, you're going to wind up with spores eventually landing. If you re-wet the wood, it can also mold and stain, but you tend to get different species colonizing, but the same problem. There are lots of species of these things. There's an estimated 300,000 species of fungi, and many of them are molds. It really, in my mind, does not matter in the least what it is. It's that the wood is wet, and you really want to get it to dry out, and that really is the problem. It's a moisture issue if you have mold. I should point out there are some species that people are concerned with. The micrograph on the right is a picture of Stachybotrys atra, which is a fungus that produces toxins in its spores and also around it. There have been lots of controversy about Stachybotrys and whether it is a deadly organism in houses. It grows on paper, not on timber. And most of the literature would say that it's really just an allergen, unless you're exceptionally sensitive to mold, in which case it does cause problems. But that's a very small percentage of society as a whole. So molds don't really do much to timber in terms of strength. So if you see moldy wood, it's still structurally sound. It's going to tend to get wet a little bit quicker. It's going to have some color in the wood, but it doesn't really affect the structure. So it can be used structurally. It just may not look as nice as clear wood. People talk about removing mold, and typically when you have small amounts of mold, small amounts of soapy water work really well with a good rag. When you get larger amounts of mold, a whole wall or a whole room, then you really want to get a professional in, because the spores can get out in the air, and these are all airborne spores. And typically you want to bring somebody in who really knows what they're doing. But we tend to recommend removing mold if you see it, just because it will cause concerns later. And even though it's not really a health risk other than an asthma, an allergen, it's viewed with some contempt by people who look at it. And it's really changed how people look at timber. Mold was not really an issue for many years. Now it is definitely something people are concerned about. We really should worry more about decay, because decay is what's going to weaken the wood. It's going to make it less usable, less suitable for what you originally designed it for. So we worry more about that. Decay is this type of internal damage here. You can see the brown fragmented wood inside this utility pole. And we worry about decay because it tends to be inside the wood where the moisture is more stable. As a result, it's hard to find sometimes. It's trapped in places and joints and timber where it's hard to get at. It all begins as spores or hyphae that land from the air, but you can also get decay moving from timber to timber. If you take a piece of decayed wood, the fungus can grow from one place to the other. They all require moisture contents above 30% and generally higher. So when you start to get decay in a building, you have serious moisture issues somewhere in the structure. And you can pretty much be sure that you have some leak or some condensation somewhere that you need to address. We have two different types of decay we typically look at. White rots, and in this image you can see the white, kind of whitish area in the center of this piece of timber. That's where the fungus has gotten in and taken out most of the structure. Typically, white rots grow on hardwood. So if you've got an old timber building like a Queenslander, we've got hardwood in a material, you tend to find more white rot. If you walk along the park and you see timber lying on the ground, often you can see it looks white and bleached. White rot fungi cause that type of damage. They're very common around Australia, really, because we have so many hardwoods. Brown rots make the wood look brown and broken. And in fact, when people first started looking at brown rots, they called the wood combusted because it looked like a campfire where the timber had smoldered and gone out, and you have all these cross breaks across the wood. Brown rots are way more important structurally because they cause really quick strength loss before you can see the decay. And that makes them very difficult to detect. They tend to be found on softwood, so a lot of the framing lumber, if it's not properly designed and used, can get brown rot decay in it. That's what we mostly worry about in softwoods. They all cause decreased strength because they attack the cellulose, and that weakens the wood. They can discolor the wood. They can also allow faster wetting, but really what we're looking at are strength losses. And to give you kind of a perspective, a brown rot fungus can cause up to 60% loss in bending at as little as 5% weight loss, which is really not visible to the naked eye, which is why when people get into looking at buildings, they're very conservative in what they'll keep if it looks like it's been wetted for any length of time. Decay is still slow, and that's a good thing. You will rarely find where a fungus, where the wood has gotten wet and it's decayed within a year. Now, far north Queensland, that would be a different situation. But if you get down into the more temperate parts of Australia, it takes years for the fungus to get going and really do its damage. So you have time to find the damage and fix it, but you do have to be on a regular lookout for it. All of these organisms have 4 basic requirements, and they're really important for understanding how to deal with timber. all the organisms require some temperature, an adequate temperature, and that's typically 5 degrees up to probably about 40 degrees Celsius. And so it's a pretty broad temperature range, but most of them have the optimums around the same places we do. So somewhere 24 to 30 is pretty typical. They all require oxygen, or most of them, all the ones I've talked about require oxygen, but they don't need very much. So it can be really low oxygen environment and they can still grow and survive. They all require food, but in these cases, the food is the timber. And so that's hard to deal with. And they all require water. And remember, we talked about the fibrous saturation point. That's the important part we want to look at. So generally, the organisms that are going to attack wood require free water. If you look at how to design with timber, it's really hard to control temperature. It's pretty bad to keep oxygen out of a building because everybody dies. And you can either deal with the nutrients, which is the wood, which we do by modifying it with preservatives or other processes, or you can control the water. And that's what your designs are all about, is trying to make sure that you don't trap water in a building. Water is really the enemy of all materials. And in this case, you can see iron and timber and concrete all really getting attacked or being damaged by wood in different ways, but the result is the same. Water is really important. It allows the fungus to swell. It swells the wood, but it also allows the enzymes that the fungus produces to break down the timber, and it also is a reactant. So it's really important in timber. If you don't have free water present, you have a pretty durable material. You can also have too much water, and if you drive by, particularly with all of the salvage material going on in some of the bushfire areas this past summer, you'll see sometimes they'll put sprinklers over the logs. That's actually to keep the wood very wet, because if you have too much water, you actually keep oxygen out. So it's a different way of getting at it. And you may say, well, why do I really care about that? I'm going to design a building. But if you go to some countries and look at older buildings, this is a picture in Venice. These buildings are built on untreated timber pilings, and they are 400 to 600 years old. And the reason they are still there is because the canals in Venice are not high salinity, so you don't have a lot of marine activity. And these timbers have been so wet that oxygen has been excluded for hundreds of years, and the timbers are still sound. So it is used in some places to protect wood, but mostly limiting oxygen is not a good thing. If you look at where water comes from in a building, it's important to look at it. You can get rain during construction, you can get leaks in service, you can get condensation from poor mechanicals. Lots of ways water gets in. Mostly though, when you look at designs, you see that people don't design with timber properly. So they create water trapping joints where moisture can wick up from the bottom and start to create conditions suitable for decay. Doors and door frames are a common one, but even designs in buildings, you've got lots of complex connections make it very difficult to exclude water. And so you have places where water can run down. And you really want to avoid water trapping joints in design. And obviously, just looking at design guides can help you with that. It happens in lots of places. This is a mass timber building going up in Oregon, and you can see that it's pretty misty because it rains a lot in the winter there. So it happens all over in terms of moisture intrusion. And this is just showing some pictures where water gets in. So you have to be careful about water because water is invasive and it will pretty much always move down. And so you really want to try and account for it in designs. So what do you do? If you have these organisms, they're always present. Termites are endemic across all of us, or most of Australia. So your risks is always there. And what you want to do is take that into account when you build your building or design your building. And there's a term called the 4Ds. Now, I have no idea who these 4Ds are. They turn out to be from the UK. But the 4Ds are really deflection, drainage, drying, and durability. And we'll talk about each sort of individually, and I'll give you some examples of why they're important. And you can think about the 4Ds later. The deflection really is about looking at a building and deciding, how do I get water away from the most vulnerable points in the building? So if you look at a building, it usually has rain screens. You've got cladding, you've got outside cladding with separations, you've got flashing around windows to shed water away. In older buildings, you'll see really steep sloping roofs to get the water away from the surface. And in older buildings, you'll see they often have verandas so that the actual structural part of the building is protected. The decking that's around the veranda may not be, and that's still a functional way to go. So deflection is really important. And to give you some examples, this is a timber frame, stick frame construction. It's actually in the United States. But let's pretend that it's built during the winter and it got wet before the roof came on. So there was 150 millimeters of rain before the roof went on. That's about 92 square meters of exposed surface area on that house. It's a lovely big house. We call them McMansions where I used to live. When you add that water to the surface of the timber, you've added 14,000 kilograms of water to about 30,000 kilograms of existing wood. The initial moisture content was 12%, which is really not what it probably was. It was probably higher. Once you've finished building that building before you put the roof on, you've increased the moisture content to 121%. So excluding water becomes important here rather than letting it in and having to deal with drying. Now, to be on the good side, this is an easy structure to dry because everything is small dimension and you can put a lot of heat on it very quickly and dry it out. But let's take that to a mass timber building. And since Adam was talking about the Monterey building, this is actually a picture from the Monterey building taken yesterday. And this is to be fair, the people building this building have really done some really careful consideration about managing moisture and durability. But let's look at what happens when timbers get wet. So this is a mass timber floor. And if you let it get wet, and let's say that I put it out and let it sit out for a month, which shouldn't happen, but often does. If you look at this graph, this is a section of mass timber that it's actually Douglas fir. It was left out in Oregon for 30 days. The solid line is the moisture content of the timber. The blue line is the amount of rainfall. One thing you can observe is the last place in the world you want to visit in the winter is Oregon. But you can see that the moisture content went from 12 all the way up to 27%. So the timber got wet, sat flat, and it increased in its moisture content. And you can see that particularly here. These are CAT scans or CT scans of cross sections of the CLT, and you can see where the moisture content went up in where the yellow arrows is. You can see the top is before and the bottom is after, and the bright white is where all the water is. So it's sitting in the timber joints in the CLT because they're not edge glued. That's a problem because once it gets in, it's hard to get out. And the implications you have is how do you re-dry that timber once it's wet without doing this to it? And so it becomes much more difficult to get water out than it ever was to get it in. So deflection becomes really important in construction and moisture avoidance. And so you're looking at things which a lot of people in Australia are now doing. Just-in-time delivery, scheduling, working with the supplier to make sure it shows up when it really only needs to be put up. Plastic wraps on the material while it's being transported are helpful. Water repellent coatings are somewhat helpful. Tents have been used. And so you see things where people want to use water repellents. And it's important to understand that a water repellent is just that. It is not waterproofing. If you look at a water repellent and you leave that droplet of water on the surface of the timber long enough, it will absorb in the wood. So it slows down the amount of water getting in, but it doesn't stop it. People do some interesting things. This was a good use of the wrapping to cap the timbers because that top cross section is much more susceptible to wetting. The water will run down inside the gaps between the edge glues, and you can get a lot of water in the timber. So putting a cap on helps. People get pretty extreme. This is a picture from Sweden, where they actually put a roof over a tent over the building as they built it. Not that practical and pretty expensive, but you can take this to extremes, but you need to consider moisture management in the construction process. It's really important to keep the water out at the start. Drainage is really important. So using things like gutters and roofs and drainage planes and walls. If you look at most of the buildings being put up now, you see gaps between the real structural wall and the cladding so that there's a place for water to run down in through the material and out the building. That's really important to make sure that those are built properly and that they're maintained so they don't get plugged up and clogged. Coatings can be important. There's a great debate about what coatings will do, and there's a lot of claims. They should protect against ultraviolet light, so they should slow down the weathering process so the wood will look pretty. They can protect against termite attack if the wood stays dry, so we see some of the H2F coatings, which are quite effective. They will degrade over time, and they must be maintained, and that's probably the biggest problem of dealing with coatings is they really don't hold up well against ultraviolet light. Coatings last, 3 to 5 years on a really extreme UV, and then they have to be maintained. And you can see that here. The disadvantage of coating maintenance, of not maintaining coatings, is that once they start to crack, they actually hold more water in, and they become more of a problem than a benefit. So you have to, when you build a building with coatings, you have to plan on maintenance. If you don't, you're just leading to a long-term problem for the future owners. The other thing to consider is that D is drying. So you want to design a building where you have airflow so that moisture can move out of the structure, and you want to make sure that your airflow is set up properly. You want to make sure that if you use membranes to control moisture flow out of the wood, that you put the membrane on the right part of the wall. You do not want to have the moisture moving to a cold surface, because it will condense and accumulate in the timber. And there's quite a lot of moisture that's built up in a building. If you look at the amount of moisture coming out from people just living in a building, it is substantial. So good mechanicals are really important in a structure. The thing I want to look at too is, how do you manage an in-service leak? So this is an example of, just to give you a feel for how much water you can develop in a building. So a small leak might leave half a liter of water in an hour. Let's say there's a cracked pipe somewhere in the building because the building is now 10 or 12 years old, things have started to settle and break. If you don't deal with that leak, you'll put in about 5,000 liters of water into that structure per year in a very localized point. So looking at making sure that where leaks can occur, you have access points are really important. So places around toilets and sinks and kitchens and dryers and things like that, where moisture will accumulate, is really important as part of that drying process. So far we haven't talked about durability, which is obviously my gig. And durability is really addressed in a number of different ways. If you do the first 3 Ds, you're really looking at durability. You're taking advantage of the requirements for decay, and you've controlled one of them, which is moisture. If you can't do that, then you have to look at different approaches. So durability really can entail a number of things: durable species, coatings and barriers, or preservative treatment. So durable species, Australia is really blessed with a lot of really durable timbers, a lot of durable hardwoods. And it's important to understand that durability is only the heartwood. So if you have that light colored wood on the outside, that sapwood, that's not durable at all. It's no more durable between any species, spotted gum versus like the Sydney blue gum or something. So you need to look at, if there's any sapwood present on the timber, it has to be preservative treated. And that's one of the requirements in the treating standards. Typically, when you look at durability classes 1 and 2, which are the highest durability classes, those are pretty suitable, and you just need to make sure that they are also termite resistant. And luckily, people a long time ago did a lot of work in Australia on this particular subject. And so Australian Standard 5604 is a list of all the species and their timber and their relative durability to termites, beetles, and also decay in ground and above ground. So there's a lot of opportunity to look at species and make sure that you're making use of a species that's fit for purpose. You can also look at barriers, and barriers mostly are really there for termites. And the idea is to keep termites from moving upward into a structure. And there's a number of different ways. If you look at an older house that's put on stumps, there are ant caps, which are just basically metal caps that force the termites to go around and out of the timber to get into the house above. And so it's not really going to stop attack. All it's going to do is allow you to find it. So ant caps are common on older Queenslanders here. There's other methods of protecting against termites. The oldest one is soil poisoning, which was used for decades and was actually pretty effective. But most of the termiticides that are used now in soil contact don't last that long, and they need to be replenished. So the alternatives that have come along are either Termi-Mesh or Granite Guard, and they're both really barrier treatments. Termi-Mesh is stainless steel screen, essentially, that's got holes that are too small for termites to get through. You put it down on the surface of the ground and basically create a barrier against movement upward. The same thing with Granite Guard. It has particles that collapse when the termite tries to tunnel. These barrier treatments are only effective if they're installed properly. And so you have to be really careful to make sure people actually do them properly. The soil poisoning, there's also ways to go back and replenish that. So these there are multiple ways to keep termites out and make sure they don't get into your building. It's important to understand too that while most termites will attack from the ground, a number can get in above ground. They are aerial nests, and so you do have to be careful to make sure that your timber is protected along the entire building. In the standards for wood treating, which is the other way we look at it, there are hazard classes, and there are 6 hazard classes, but for intents of most buildings, we really look at 4. And 1 and 2 are really places where the timber is going to stay dry. And with 1, you have the risk of beetle attack. With 2, you have the risk of termites. And so for many of the houses that are built in particularly the northern part of the country, you'll see the framing is treated with a bluish or a colored chemical. And that's a termite treatment specifically for framing. And it's a barrier treatment. It's there to keep termites from getting in. It's not for decay. It's really only for the termites. When you get into more exposed areas, you get into hazard classes H3 and H4, then you're looking at much more significant preservative treatments. And we won't get into 5 and 6. The traditional treatments are really, as I said, H2 is really there for spray on or dipping for coatings, and it's a barrier treatment that's intended to keep termites away, and it's quite effective when it's done properly. The other treatments are usually applied either using long dip cycles or pressure cycles, and the idea is to force the chemical deeper into the wood. These are specified in the standards, and there are 2 basic materials that are used now for treatments. We have light organic solvent or LOSP treated azoles, which are clear, and you typically will see them in decking and cladding. And then there's copper-based systems, and those are ACQ, which is a copper compound with a quaternary ammonium compound or copper azole. And all of these will work against decay fungi and termites. And so they're there to basically protect wood where you aren't going to be able to keep water out. You're going to have it exposed, and you need to make sure that it's going to be protected for a long period of time. The other things that are coming along are modified woods. And modified is something where you're not really using a pesticide, which would be the other chemicals. You're trying to change the wood structure itself. And the 2 that are commonly seen in Europe are acetylation and furfurilation. Acetylation is Accoya, and Kebene is the furfurilated material. Accoya is basically reacting the wood with a chemical that takes away parts of the chemistry and makes the wood less likely to absorb water. It has been used in Europe for about 20 years. It is really only becoming much more commercially relevant now. It is sold in Australia, and it has done reasonably well against termites and decay fungi. And it's just the disadvantage really is that it's much more expensive, but it will work. And you see it used in exterior cladding on sort of some of the high-rise buildings. Kebene is not widely sold in Australia, but it is becoming more common, and it's sort of a reaction product. You bulk the wood, you fill the wood with furfuryl alcohol, and you heat it to fix the material in. So you basically block the water out of the wood by just filling the cells with the furfurylated material. And we're about to put it into test, but it's something that is done well in marine environments and decay environments. The third one you'll notice I have in very light blue, and it's because thermal modification has been around for about 70 years. It's not a new treatment. It was originally developed for modifying woods to make them darker, to make them look fancier. It does modify the ability of water to be absorbed in the wood, and so it changes the water holding capacity of the wood. And it is being sold in Australia right now as thermally modified wood. The disadvantage of this particular material is it is not at all termite resistant. And so if you get into an area where termites are present, it needs supplemental treatment. And there's at least one product on the market where they have thermally modified wood, and then they pressure treat it with LOSP to make sure that it will work. And so you want to be really careful about thermal modification, because if termites get in, there's some evidence that they'll actually attack it more aggressively than they would the non-modified wood. It does make the wood last a little bit longer, but not as much as the pressure treated wood would do. So it's an interim place. It's used a lot in Europe right now, where the decay conditions are a lot lower, and there are no termites in most of the areas where it's present. So if you look at the options here, you have a lot of ways to get it making a durable building. It's really integrated. You don't have to use everything in every building, but you need to consider all the aspects. Where you can control moisture, you're going to do it through design or barriers. You can do that, but then at some point where the building is going to be exposed to the elements, you really have to look at durable materials, and that can be naturally durable timbers. It can be chemically treated timbers, chemically modified. You really want to consider them all before you put them in, and in the end, it probably comes down to cost more than anything else. But they all can work in the right environment. You need to carefully construct. It's really important to understand that you can design the best building in the world, but if somebody takes it and doesn't understand what you're trying to do, invariably they will not do it the way you want it. And there are many instances of failures in buildings where, in a complex of buildings, where a misapplication of a design didn't just happen once, it happened hundreds of times across the complex. So you want to make sure that the instructions are clear, everybody understands why you're doing what you're doing. And then the other important part of this is we don't build things and expect to walk away from them, but we often do that with timber. Timber needs to be maintained just like every other building material. And it's important to make sure that that's built into the design so that people understand that it isn't just a open, turn the key and walk away. You really have to do that. And if you do this properly, one of the things you can get is often people say, well, what is a 50-year building? I have a house back in Oregon that's 107 years old. It's the original timber. It's as sound as the day it was built because it was built properly and maintained. And with any building, you can do that if you do it properly. And it doesn't matter what the material is, it's steel, concrete, or timber. If you do it properly and you maintain it, they last. And so when you look at a timber building, it is just as durable as any other material on the planet when you do it properly. So with that, I would conclude and ask if there are any questions. If you want more information or want to get our newsletter, which is a quarterly newsletter, the website linkage is down below. You can sign up there, and I'd be happy to answer questions if I can figure out how to make it work. Thank you.
Thanks so much, Jeff. That was phenomenal. If you just hit the Q&A tab, a few questions might come up.
Where am I going?
And whilst you're doing that, I might.
All right, what just happened there? I got Q&A. There we go. Cool.
There we go.
Questions.
I'll kick it off with the first question, Jeff, and I'm taking it from Jeremy Church, who might be familiar to everyone, who presented for us a few weeks ago for an engineering topic. But he asks, in your view, what role, responsibility does the structural engineer play in achieving the design life for 50 years? So from his perspective, there's a bit of grey area between whose responsibility is it? Is it the architects or is it the engineers? And how much is it to do with the engineer?
I have the opinion that we're kind of all in this together. I think the engineer has a responsibility to sort of alert the architect about design flaws that are going to cause problems. I think to not do so is sort of abrogating some of your responsibility if you know better. And one of the problems we see, and I know the Wood Solutions seminars are trying to address that, is a lot of people come into timber without a good background. And they've gotten a lot of concrete and steel in their education, but not as much about timber. And it's really important to help them to learn what they should do so they don't have to learn by mistake. So I think we're all part of that. Will termites attack charred wood? There's the what is it, Sho Sugiban. I don't honestly know. I want to put some out and test. I think they will go through it. I think they'll sacrifice workers to get through it if they have to, particularly the more aggressive, like the copper termites. So I'm suspicious that that's going to work really well. I'm also suspicious that it's going to work for keeping decay out. Cracking, I'm not sure about the plasterboard question because that's not my area. If it swells up enough, though, I mean, it's a pretty rigid material and it's going to pull the plasterboard apart.
I've got a question here for you, Jeff, from Callum Lillywhite. What are your thoughts on the degradation of internal timber behind a glass facade exposed to some sunlight for parts of the day? So I'm assuming it's obviously not exposed to the weather and moisture.
Yeah. Well, I think you'll gradually get some UV going through the glass facade. It's not detrimental to the structure; it's just detrimental to the appearance. And you'd have to look at some type of a UV protective coating over time, but it's not going to hurt the wood per se. In fact, we have, I should say, back because I've only been here for about 2 years. In Oregon, we have some tests going on coatings, and one of the things that's just fascinating is how quickly they degrade.
Yeah.
The full UV exposure.
Interesting. We've got a question here from Jane Armstrong just on that. She asked, do coatings need to be maintained only if the timber is external? And are coatings required for internal timber?
I probably wouldn't use a coating for an internal timber unless I thought it was going to be exposed to some element. But the coatings exterior clearly, obviously, need to be maintained. And they do go quickly.
If I could just get you to ask, when you read out the question, just the name if you've got it there as well.
We're going down, I'm just trying to go the in-ground stump durability. If you look at the durability classes 1 or 2 and H5, I mean, they'll give you the lifespan depending on, either 15 or 25 years or better. And it really depends on the species. That would be, 15 years on a stump would be relatively short, but depends. I think the other thing we're looking at is how durable are timbers these days. That's a different problem. And I can move. I didn't realize I had control of that.
Got a question here. Yeah, when new questions come through, it changes the order. I've noticed that. There's a question here from Martin Bursey. What's the hazard to humans with chemical treatments in H2 and H3, if any?
Pretty low. So the chemicals that are used for H2, it's an insecticide, and it's got a fairly low vapor pressure, so the risk of exposure in a building is pretty low. The H3 chemicals are, the clear ones are triazoles. Triazoles are used in lots of over-the-counter medicines, particularly controlling athlete's foot. Is a real common one, fungal infections. So they're chosen specifically because of their low toxicity to humans. So the risk to humans is pretty low. And generally that's why they've been used. The question about detailing, I think there's good details to follow. I think the changes we see are that the amount of training people get is probably a lot lower than it used to be, and that's not to be unfair because there are really good craftsmen out there, some really good chippies. But I think it's more our expectations are lower in terms of what people learn. There's a lot of good information on proper design and detailing.
So we'll take 2 more questions, Jeff.
Yeah, just looking down to see the Akoya. Akoya, the question was, what do you do to keep Akoya from going gray, or how do you keep it from staying gray? One of the disadvantages of Akoya is it's not very resistant to mold, and so it will tend to gray and mold, and so it's hard to keep it from going sort of gray black. It's not going to hurt the wood. It just doesn't look as nice as it did when it first went in, and I'm not sure how you can get around that. I've seen trials of trying to do that. They haven't been highly successful. And where are we going? What else?
I've got a question here. If you clarify the difference between the durability of LVL and glulam. So 6 people upvote this one. Yeah.
So the H3 durability for LVL, as long as it's properly treated, it should do well. If it's not, it won't. But we just had this discussion. Actually, they're having this discussion in standards right now about treating glulam, because if you're treating glulam, you're supposed to treat the individual lamina to the standards for the individual pieces. And so if you have a well-treated piece of glulam, it's going to do pretty well. The same thing as if you have a well-treated piece of LVL, but you have to make sure it's properly treated, and glue lines can cause problems in LVL. So it's important to make sure that it's really inspected and that it's treated properly and inspected to make sure that it's actually fit for purpose. But if it's properly treated, it should do well. What else we got?
Fantastic. So we'll take 1 more.
Sure. You want to do the strength one? So the strength reduction one is interesting. If you wet wood and dry it, it doesn't get weaker. If you age wood, it really doesn't get weaker. But what you may see in reduction in properties will be if it wets and dries, your fasteners will behave differently. So it's the connections that probably become more important. And what you see, at least in some of the testing we're doing now, is initially you actually get a little bit of improved properties when you wet and dry, but then you'll see a gradual decline with wetting and drying because you're basically pulling the fastener away from the wood. And so that's why when you start looking at material that's been wet and dried a number of times, you start to become suspicious about its properties when it was designed for interior use. So, but just wetting the wood and drying it, you may get more checking, but it shouldn't really change the overall properties of the wood.